In our quest to build the best sub 250 gram FPV quadcopter with the highest thrust to weight ratio, we've come up with an amazing combo on 3.5-inch propellers, achieving both a practical and efficient thrust to weight ratio of over 11:1. In our last 4-inch propeller test video, we tested various 4-inch propellers on a T-Motor F1408 3950 kV motor, where we concluded that the kV may be too high for this propeller size. In this video, we will take the same motor at a lower rated 2800 kV and see if this combination can finally give 4-inch propellers the edge.
Recursion Labs. For science.
This testing will be conducted on my updated variable controlled motor testing methodology, which you can learn more about in the video linked in the description. These tests were conducted at 16 volts to emulate a 4S battery. For 4-inch, we'll be using the T-Motor F1408 2800 kV motor, tested at an actual 2871 kV, and we'll pair it with HQProp 2-blade 2.5-inch pitch propellers, Gemfan Hurricane 2-blade 2.4-inch pitch propellers, Gemfan Hurricane 3-blade 2.3-inch pitch propellers, HQProp 3-blade 2-inch pitch propellers. We will compare them against the current 3.5-inch performance and efficiency leader, the T-Motor F1404 3800 kV, measured at an actual 3772 kV, and will be paired with the HQProp 3-blade 2.5-inch pitch propeller. The 2-blade 4-inch propellers are almost the same weight as the 3-blade 3.5-inch propeller, and the 3-blade 4-inch propellers are both almost half a gram heavier. We'll talk more about weight later, but before that, we should look at thrust. This is closer than I thought it would be. Like on the 3950 motors we tested previously, the Gemfan 3-blade highlighted here comes out as the thrust leader, taking a progressively larger lead starting at a 35% throttle. With that said, the current 3.5-inch performance leader highlighted here has the lead before that until slowly losing out to all the 4-inch propellers tested. This is a huge blow to the 4-inch at the lower throttle, but may be redeemed when looking at efficiency. So let's do that now. Now this is really interesting. The 3.5-inch leader overall generates less grams of thrust per watt than the 4-inch propellers, but it starts off with an impressive lead until around 25% throttle, where it ties and becomes worse the more throttle you give. This means that hovering and light cruising, the thrust of the 3.5-inch beats the 4-inch setup. This is probably less of a win for the 3.5-inch propeller size, but more for the HQProp 3-blade 2.5-inch pitch propeller specifically. Not surprising, the 2-blade Gemfan leads for efficiency after about 30%. What is a bit surprising is that the Gemfan 3-blade beats both the 2 and 3-blade 4-inch HQProp at the low end, and ties the 2-blade in efficiency for the rest of the throttle range. Now for the most important chart, grams of thrust generated to watts of power. So this is interesting. You can clearly see the advantage 4-inch has here, being able to generate more thrust for the same power after what appears to be 200 grams of thrust. And at the low end, the 3.5 wins out until around 50 grams per motor. The Gemfans both take the lead. HQProp 4-inch are the worst here still, but eventually beat the 3.5-inch after about 80 grams per motor. Regardless, the difference down here isn't massive. Up here it is. So let's talk about it. Let's remove everything but the 3.5-inch and the 4-inch 3-blade Gemfan, as this is the most interesting to compare to. So, the 3.5-inch wins slightly at the low end, but the 4-inch generates a lot more thrust for the exact same power, about 110 grams per motor to be exact. For free. Wait, no, this isn't free at all. Now that we have this data, we can finally talk about weight. Here is a data set I'd made with my current 3.5-inch scythe build, which I made to help compare against potential new sub 250 gram designs. This takes the battery cell count, size, and weight, along with the frame weight, component weight, rotor weight, and the weight of the propellers, to all combine up into the all-up weight. With that, we can calculate the two most important data points. The first data point is calculated from the size of battery, multiplied by the cell count, by the max wattage for all 4 motors, which allows us to directly compare the output potential of all batteries across different sizes and cell counts against the maximum power demand of all the motors. If that's confusing, all you need to know is the higher the number, the more a battery can deliver at max throttle. Between 8 to 10 is probably a reasonable target. The second data point is a thrust to weight ratio, based on the maximum thrust output of the motor. So, for the 3.5-inch scythe build, we have an all-up weight of 155.6 grams for a total of 1.76 kilograms of maximum thrust, which gives an impressive thrust-weight ratio of 11.3 to 1. Now, we can plug in the 1408 2800 kV 4-inch numbers for the 3-blade Gemfans. The top wattage is similar, so we can keep the same battery, and keep the same component weight. We will add 6 grams to the frame, assuming it would be the same lightweight frame, but with longer arms that are maybe a bit wider to handle the additional weight, which could even be a bit liberal. The 1408 motors are 5.6 grams heavier per motor, and the propellers are 0.46 grams per propeller. propeller. This would give us an all-up weight of 185.8 grams, which for a 4-inch would be fairly good. The per cell milliamp hour per watt is about the same, and the thrust-to-weight ratio is slightly higher at 11.8 to 1. On paper, this theoretical build actually sounds amazing because it's lightweight for a 4-inch and has an impressive thrust-to-weight ratio. But does it make sense over the 3.5-inch build? Let's dig a bit. The small boost in thrust-to-weight ratio is nice, but it isn't significant, and it only represents the maximum. Looking back at the previous graph, we can see that the lead the 4-inch has over the 3.5-inch is diminishing the further down we go until the 3.5-inch takes lead. This means eventually the 3.5-inch generates more thrust for the same power and weighs less. I tried to think of the best way to show this, so I've taken the original thrust chart, leaving only these two motor and propeller combinations, and multiplied the thrust by the weight difference to make it easier to make the thrust comparable as if they were the same aircraft. And here's the result. We can now see that the thrust to weight potential of the 3.5-inch beats the 4-inch across nearly the entire throttle range, or for around 78% throttle. If we do the same thing with efficiency, you can now see that the 3.5-inch setup is significantly more efficient, where you would spend most of your time on the throttle, and only starts to become less efficient at around 80% throttle. So, with the exception of the absolute top end, the actual performance and efficiency is better on the 3.5-inch build compared to the theoretical 4-inch build, with the additional bonus of being more agile due to the lighter weight and is probably quieter. Smaller is better. I hope this information has been useful and helped demonstrate the delicate balance when choosing components and the importance of this type of testing and doing that. I've not entirely given up on 4-inch yet. This isn't going to be easy, and there still is 5-inch, so more to come.